So, what if we could train AI to be fundamentally smarter, not just bigger? Well, a new paper is proposing a pretty revolutionary way to do exactly that. It's called semantic tube prediction, and it might just make AI more efficient than we ever thought possible.
Let's just jump right into the headline claim because, wow, it is a big one. I want you to imagine an AI model that gets the exact same performance as its peers, but with only 1/16th of the training data. That's the core breakthrough here, and it really challenges some of our most basic ideas about how AI gets better. To get why this is such a huge deal, you gotta understand what we call the scaling law problem. For years, the playbook for building better AI has been pretty simple. Just add more. More data, more compute, bigger models, a brute force approach. And hey, it works. But it's incredibly expensive and, as this research points out, maybe surprisingly inefficient.
And a lot of that inefficiency comes from the standard way we train AI, a method called next token prediction. It's basically like teaching an AI to finish your sentences, one single word at a time. The problem is, this method is super noisy. The AI really struggles to separate the true meaning of the sentence, what we call the signal, from all the random statistical junk in the data, the noise.
Okay, so to fix this, the researchers are asking us to think about language in a totally new way, not as just a chain of words, but as a journey.
Think about it like this. Imagine a giant map where every single concept has its own location. In this view, a sentence isn't just a string of text, it's a path, a trajectory that your mind or an AI takes through this vast landscape of meaning.
And this is where it gets really interesting. Look at how this visualizes that path. The most direct, the most logical and error-free route between two concepts is what mathematicians call a geodesic. For example, the conceptual journey from Paris to France has the same basic shape as the journey from Rome to Italy. It turns out there's a real geometric structure to meaning itself.
And this brings us to the core idea of the paper, the geodesic hypothesis. It basically says that the clearest, most logical train of thought follows the straightest possible line through that map of meaning. It's an idea borrowed straight from physics, the principle of least action, which suggests that nature, and maybe language too, is just inherently efficient. So, if the perfect path is a straight line, how in the world do you get a learning AI to stick to it? Well, that brings us to the really clever solution these researchers came up with. They call it the semantic tube. Let's break this down. That orange line in the middle, that's the perfect, ideal path, the geodesic. Now, see all those scattered blue squares? That's the model's actual internal state as it's processing a sentence. They're kind of messy, right? They wobble all over the place. The semantic tube, that light blue cylinder, acts like a set of guardrails. It's a brand new training rule that penalizes the model anytime its path strays too far from that ideal straight line. This visual makes the idea perfectly clear. Any forward progress inside that tube is the signal. That's the real meaning we want the AI to learn. But any movement away from that central path, that's just noise. It's a statistical distraction that the model needs to learn to ignore. So how does this actually work in practice? It's surprisingly elegant. The AI trains just like it normally would, but now it has a new rule: stay in the tube. If its internal thought process starts to veer off that straight path, it gets a tiny penalty, which nudges it back on course. This literally forces the model to focus on the signal and filter out all that distracting noise. Okay, so that's the theory. It's clean, it's intuitive, but does it actually work? Let's get to the results, because this is where it gets really, really exciting. 16 times. That's the number that just jumps off the page in this research. 16 times more data efficient. So let me put that another way. An AI trained with the semantic tube can match the accuracy of a standard model, but with 16 times less training data. I mean, that is just a staggering leap in efficiency. This graph from the paper tells the entire story. Just look at the orange line. That's the model trained with the semantic tube. As you move from right to left, dramatically cutting the amount of training data, its accuracy stays incredibly high, super stable. Now look at the blue line, the standard model. Its performance completely falls off a cliff as soon as you start taking data away. And it's not just about efficiency, it's also about peak performance. On this particular dataset, the standard model just kind of plateaued at around 57% accuracy. But by adding the semantic few, that number jumps all the way to over 84%. So the model learns faster, and it ends up learning better. This is why the authors make such a bold claim.
They say this result directly violates the data term of chinchilla-style scaling laws. Now, you have to understand, those scaling laws are basically the industry's rulebook. They dictate that to get more performance, you must have more data. And this research comes along and proves there's a smarter way to scale, a geometric approach that just breaks all the old rules. So if we look past the impressive numbers for a second, what are the bigger implications here for the future of artificial intelligence?
Well, first, it promises much more efficient AI, which could slash the cost and energy needed for training. Second, it shifts our focus from just making AI bigger to making it smarter. It's a move from brute force to elegance. Third, it actually preserves diversity in the model's outputs, helping it avoid something called mode collapse, where it just gets stuck in a creative rut. And finally, it offers this beautiful, unifying theory, tying together a bunch of different ideas about AI learning under this one powerful geometric principle.
Let's look at a really concrete example of that diversity point. In one of their tests, there were 2 ways to write the same code suffix. The first way was 35 times more common than the second. The standard model, it struggled to learn either of them correctly. But the semantic tube model learned both the dominant pattern and the rare one with really high accuracy. It understood the underlying concept, not just the surface-level statistics.
So, ultimately, what this research is really suggesting is that the path to better AI might not just be about better engineering, but about better science. This isn't some simple optimization trick. It seems to be a fundamental insight into the geometry of meaning and learning itself. Which, of course, leaves us with one final and pretty provocative thought. If forcing an AI to follow a straight path through a map of meaning can lead to such a massive breakthrough, what other profound secrets about the very nature of intelligence are still out there, just waiting to be discovered, hidden in the language of geometry?